So we're given a jet of water that is moving at 30 feet per second, and it is hitting a completely vertical plate, and the water is just directly splashing kind of up and down along this vertical plate. The whole system is stationary as there is a force of 500-pound force being applied to the other side to counteract the force of the water pushing onto this plate. So our goal is to find the volumetric flow rate of the water. So how we're going to solve this is using this steady linear momentum equation. And this equation is actually really nice. It's kind of simple in a weird way, but it looks a little bit weird at first. So first of all, our beta value is the thing that kind of stands out when I at least look at it. That is what is called our momentum flux. And our momentum flux, in the long story short, if you watched my previous video where I talked about alpha and that correction factor, it's very similar to that, just kind of adding in a little bit of extra stuff to cover up for some things that are not perfect within our system. So that's essentially what our beta is. In this case, I'm just going to assume beta is equal to 1 for simplicity. But looking at this equation a little bit more, all of these are our external forces, and everything else, all of this is for our flow. So we have all of our flow going out and all of our flow going into the system. So what is the system? Well, it varies per problem. In this case, we have a jet of water and then it hits this. So obviously I would not take my system over here as I don't know what it is. It could be the 500-pound force could be coming from a support beam, or it could be someone holding that 500-pound force, or I should say pushing it. I really don't know, but what I do know is that there's some kind of force happening over here, and we're given everything on this side as well. We're not given like a hose or anything to where we need the pressure inside it, but yeah, we'll just kind of use, say, linear momentum equation, and our goal is to find the volumetric flow rate. So that's kind of what we're going to do. We have our system right here. Be very careful whenever you're selecting your system. I'm just going to kind of draw out where I'm thinking my system is. There's no hose. It just kind of goes up and down across this vertical plate. And it also includes this force, I should say. So let's just get solving it. So this is a horizontal jet of water, which means that we only have to deal with things in the x direction. So everything will just be along, our horizontal direction. If this was an x and a z, where we had something in a two-dimensional plane, or even if we had a y, then we would have to kind of split this up into here are all of our x's, here are all of our z's, here are all of our y's, and go from there. In this case, though, I want to choose a problem that was only in the x's, just so that you kind of get the idea of it. But if you were to do this in multiple dimensions, you definitely could. It's just a little bit more calculation. It's similar to engineering statics in the sense like extra dimensions don't really hurt, they just add in more time. So all of our calculations are in the x direction. So what I'm going to do is I'm going to define which way is positive. So our direction pointing to the right is going to be our positive x direction, as that is where it's hitting the plate. So writing out this equation, let's do negative 500 pound force, because remember, this is our external force. We have 500-pound force going against our positive x direction. So negative 500-pound force is equal to what going out? So what's coming out of the system? Well, we have the water, and it goes from here and it goes up and it goes down directly. Well, in a weird case, our out is actually going to just be in the z direction. This is a two-dimensional problem. However, that is going to be canceled out on both sides because we're going to have flow going up here, we're going to have flow going down here. All of that will just kind of cancel each other out. So all we're left with is our x. So going back into one dimension apparently. So for our out, we actually have nothing because our out is only in the vertical direction. What we do have though is our in, which I'm going to put in green. Our in is what we have. So go over here and we say that our out is 0 and our flow coming in is going to be beta, which I've already determined is 1, times our mass flow rate, which we'll need to find, times our velocity. And our velocity, we are given it at 30 feet per second. And we have to remember that this is going in the positive x direction. So everything inside of here, imagine we have some extra brackets. Everything in here is positive, so we are still subtracting. So let's go ahead and solve for m dot. So let's go ahead and do 500-pound force, and we divide that by negative 30 feet per second. So this would be 500 over 30, which is 16.66, repeating, pound force seconds per feet. That is not what mass flow rate should be, because mass flow rate is pound mass per second. It's mass per unit time. So we can probably convert this. If we look at this conversion right here in saying that 1 pound, I actually don't like how all that is in res. Let me just write it in white down here. 1 pound force is equal to 32.2. See if I can remember this. Pound mass per foot over second. I want to say second or maybe second squared. I want to say it's second squared actually. So we can use that and try to get rid of our pound force value. So we can do that by multiplying this by 32.2 pound mass per foot second squared for 1 pound force. So canceling out units, feet cancel. That cancels. And then our pound forces cancel, which will give us pound mass per second. So multiplying 16.667 by 32.2 would give us 536.67. Move this over a little bit. 536.67 pound mass per second. So just a little bit of a quick recap on why I did all of that, because I just realized how fast I kind of went through that. Let me just kind of go through the entire problem from the from the top. So we go over here, we realize that we need to use the linear momentum equation. We set up our equation. This is our non-fluid number, non-fluid forces, which is all of these. We have nothing going out in the x direction. Our z direction, our up and downs cancel, so all of this is only in our horizontal direction. or say all of this is in a horizontal direction, this entire equation. For flow going in, we have whatever's in blue right over here. We have 30 feet per second, which is given. We have 1.0, which is our beta, which I've determined that to just be 1.0 just to make the problem easier. But normally if there is a beta, it would be given. And we're solving for m dot. Going ahead, solving for m dot, we had this very weird unit, which is not very nice, and we used this unit conversion I've circled in blue. This is one of the best unit conversions for the English system. I really recommend getting to know it well. As you can see, kind of how helpful it is, getting us from feet-pound per second, pound force times seconds over feet into pound mass per second, which is much better unit to work with. So the reason why I'm solving for our mass flow rate is that mass flow rate is equal to the density times VA, which you might also recognize as the density times our volumetric flow rate, which is our goal for the problem. So we know the density of water in this system is 62.4 pound mass per cubic foot. So what we can do is solve for our volumetric flow rate using the density of water, plugging that in right here. We have our mass flow rate, which we have just found right here. And we should be able to solve for V dot by doing m dot over rho. So 53.667 pound mass per second divided by 62.4 pound mass per cubic foot. Check our units. Pound mass is canceled. This cubic foot will flip to the numerator. So our answer will be in cubic feet per second, which is exactly what we want. So divide 536.667 by 62.4, and that should get us a volumetric flow rate of 8.60 cubic feet per second. So that should be our answer.